Hi everyone, sorry about the delay. We'll start the next talk right now, and we're going to have Chuck-jee Chau talking about algorithmic artistry, musical ideas for Pythonists. Thank you, Chuck-jee. Please welcome him.
Hello everyone. I'm really glad to be part of this event because after all, I don't consider myself as a developer in Python. I teach a little bit of Python courses in university, but that's all. I only know introductory Python and a little bit about music as well. So I hope to share with you a little bit on music-related Python libraries. After all, this might be something more relaxing after your whole day of long talks of very technical Python ideas, and now I'm trying to make it more technical for musical ideas. So in case you are curious about me, well, just do a Google search, will be easy enough to figure out that. All right, so you can do that yourself. And in case you enjoy working on collab notebooks, you can easily access this notebook as well using the link or the big QR code. I don't know why it's so big anyway. Yeah, feel free to run some code because I figure out that interaction might be something more fun to engage students after all, so that they can play something other than just playing on games or something while they are listening to classes. So yeah, and unfortunately, I find that quite a lot of the libraries that I would like to introduce cannot really run on the collab environment. So I try to put it quite simple into more fundamental ideas about sound and music. Right, so I guess this is kind of okay in case you are not able to get this. This is just a PyCon 24 minus music, then you can get this notebook. All right, so let me give you a very, very brief introduction about what computers are there in the role of music making. So computers can be an instrument. They can make new sounds. After all, traditional violin or piano playing could already been there for hundreds of years, and nowadays people are not really happy with just traditional sounds. They had in a lot of new sounds, and computers are there to generate new kind of timbres, new kind of tone colors that we are able to use them. And computers could be some new medium for us to express ourselves, so that we can use the computer to generate new multimedia forms so that we can interact with the user. The users can type code and generate some of interesting artworks as well, right there live coding in front of people. So computers can be tools that we can easily help, for example, an orchestra to play music. For example, when I was a keyboard player in a musical theater work by, for example, Chungying Theater a few years ago, we had to pretend to be violin, trumpet, all kinds of sounds because apparently they don't have the budget to hire a whole orchestra to play for their theater. So we have to use technology to save money, to get a small band, which sounds like a huge orchestra. And yeah, of course, nowadays people are talking about computer as a player to replace human. Just like when ChatGPT is out, everyone is thinking, oh, are we going to be replaced? Same as musicians. After all, do you really want to hire a whole orchestra while you are using the washroom? No. So you might want some other technologies to help you. And of course, we do want computers to help us compose as well. And all these ideas actually start from machine listening. We have been talking about machine learning for so long, and we have to let the machine learn about listening as well so that it can generate sounds and music. But let's just start with the fundamentals. In case I try to blend a few different notebooks and a few different ideas together. So for more details, you can easily refer to some of the links I attach here. And I found that the Wi-Fi connection doesn't make my running of code very smooth, but I will still try to run the code with you. After the talk, I will try to put down my words back into the notebook so that it's more informative by itself. But at least, at this point, let me just talk through it. Basically, I'm sure you guys understand about NumPy, IPython, Matplotlib. All this has been around for quite a few years. But we do have something new here, librosa. I will tell you more about this library quite soon. And here I would like to import math as well and set some parameters. So let's start with sine wave. So I'm sure you have heard of sine wave, which is in the curriculum of secondary 2, secondary 3 students, and we are always making sine wave in computer music. So in order to generate sine wave using NumPy, we can simply set it up using the formula 2 pi frequency multiplied time. So it's a time series. I saw some of my students here, and I'm sure they have already learned a little bit about this. And basically, after we are able to make some sine wave, it can look like this. And this is just a sine wave of 440. In case you have been to an orchestra play before, you might be able to recognize this pitch. Of course, it should sound a little bit better, but this is what the computer makes in its most simple form. So that's called a sine wave, and it's boring like this, up and down, 1 to -1, and that's all. After that, we can actually create something more by introducing all other kinds of frequencies. So if we run this, we are able to make some C, D, E, F, G. You know, musicians only know 7 alphabets. We do not need to learn more than 7. So C, D, E, F, G simply sounds like this. Yeah, so that's all we want, that we are making sounds like this. And if we are stacking them together, we can make something more complex, and that is called additive synthesis. Unfortunately, I don't think I can cover it in 5 minutes, so here is just the code to help you understand a little bit about this multiplication, stack them together, all right? So add it to the output. That's all we are doing in the additive synthesis. So they are multiplied together with different ratios of amplitudes in order to generate some sounds. So let me recap with you how one single harmonic sounds like. So it works like this, sine wave. Right, it's nothing more than a simple, boring sine wave. But when we are adding a longer list, I believe I do not need to introduce to you again what is a list. So here are some more amplitude ratios that we are using. Some of the harmonics are louder, some of them are softer. And we are able to create this new waveform, and it looks like this. So I believe you would think that this sounds more complex, but it still sounds like beep. So it might be a little bit different. So it's all coming from rudimentary Python. No library yet, except NumPy for numerical manipulation. So here we are just trying to replicate something more. Well, in order to make music, we do not really want to always just type all the frequency values. That's too tedious. So we will set up some basic functions to help us so that, like, where am I? Here, pitch to frequency. And then I can set up also a function to play a melody. After that, let's try to work on this. So this is a list of pitches to play in MIDI numbers. So MIDI is another big standard to denote pitches, instruments, loudness, durations, etc. using computer format. It is a very old format. It just got its second version a few years ago, and the first version was older than me. So you can see that it's pretty stable actually. So we can see the multiply function, which is for the duration as well as the harmonic ratios. And this sounds like something more fun, which is, make a guess. Right, so just numbers, and we can already create a nice music. All right, so there are quite a lot of good libraries that you can try, including PYO or PyO and Pedalbot. These are some famous libraries that you can try to explore. Unfortunately, PYO is not working on the notebook platform, so you can try on some kind of standalone Python installations. Great, so I'm already using 10 minutes, good timing. So the second part is, let's try to take a look into the information inside the sound. So this is based on another notebook. You can see that this is a website called musicinformationretrieval.com, and indeed this is going to recognize some sounds. But before that, I would like to, I found that it's not easy to prepare some audio right inside the Colab environment. So I'm using this recording mechanism. I hope that it's going to work because I still have no idea why sometimes it's not working. So let me try to record. I have to allow this. Da 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 da. Yeah, looks like it succeeded. Let's see if it successfully loads. In case you are trying this at home later, and the recording thing is not working, it's not my fault, unfortunately. And you can grab this WAV file from the original author, not from me. So you can try that as well. And we are going to do a little bit of analysis on it. And I will load this file and take a look. Oh, it can be played. Great. So let me hear my own singing embarrassingly. Da, 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 da. Oh, it's not capturing the front part. It's okay. I am well prepared. And let me just replace it with another recording that I made a little bit earlier. Okay. Should be there. So I try to load it again and play again. Da, 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 da. Okay, I better delete this file and upload. Sorry about that. Things never goes very easy for live demos, unfortunately, for all our multimedia presentations. Let's try once more. Run this. And la 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 la. Okay, I don't think you need amplification of that, so you can kind of expect what that is. Well, that's for a normal user, ordinary user. So let's see what would be sounding like. I also want to trim it. That means to take away the parts which are empty. This is not doing a very good job yet because after all, this is kind of noisy in the recording environment because of the AC, because of buses passing through. La 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 la. Right, so of course, usually we prefer to look at it, and this is the waveform. And this lip roser, kindly prepared by the Columbia University, they have a lab that they are called lab roser. So that's why they call the library lip roser. And it's very popular in music information retrieval community. And the waveform is like this. Basically, I'm sure you recognize it when you are sending WhatsApp messages in voice messages. Some people hate to see it. While you are recording voice, usually this denotes the loudness and the soft parts. And we can also try to calculate and find out a amplitude envelope, which basically follows whether it's loud or soft, which is useful for scaling later. And well, for scaling, 0 to 0.15 is not very good, so I can normalize it. The good thing for LibRosa is that it provides basic NumPy compatibility. So anything that you want to numerically manipulate is easily compatible with NumPy as well, so that you can see all this NumPy max, NumPy min can easily be applied into this data that we collect. Apparently, I didn't sing very well. Some of the notes are softer and perhaps too embarrassed when singing to the sounds, but it's okay because all we are going to do is to check out the frequencies. So frequencies are like the very beginning numbers that we started with. 440 is A, and then we also have 261 as a middle C, something like that. And we would like to plot it out using a spectrogram. So there are some more technical terms here. And in this spectrogram, you can see the together with some noise and also some more harmonics. And that's actually about the additive synthesis. If we are able to stack all these harmonics up it can almost recreate my voice. Of course, a lot more work is necessary, and I don't think I can cover it in 10 minutes. So you can try to look for that yourself. And on this chart, on the vertical scale is basically the notes. So roughly this is a G between the C and the C. And then I can try to detect where the notes are by doing some onset detection. So basically all these peaks denotes when the notes are starting because they are representing the stronger energy. So we can further detect the onset using a lot of peak finding algorithms in LibRosa so that we can find out where the samples are and where the boundaries are. And finally, we can plot it together with the waveform. So in general, these are working pretty nice, and you can see that all these spikes inside the waveform are recognized. And indeed, we are relying on them to estimate the pitch. So we will use some more functions like autocorrelate function in LibRosa for detecting the fundamental frequency, that is the pitch that we are hearing. And in this example, we can regenerate the detected pitches into a sine form. And it's going to together generate a list of frequencies that is detected as well. And luckily, it sounds pretty good. It's not the best, but at least it tries to capture, and it can also generate this frequency list. But this is not very user-friendly, not very musician-friendly. So we can generate it back to a note list using LibRosa helper functions so that there are the noises in front and also this. Apparently, this is not very much like what I want, so I want to take away the noise in front. So I just use Python slicing. It's easy enough to get rid of something you do not want. And oh, by the way, the regenerated sound can look like this. So it looks much cleaner. So you can compare this with the spectrogram that we have made in front. It's kind of the same with the ups and downs, but now that it is a sine wave, it's much simpler. And we actually made the amplitude envelope earlier, so this is useful to scale this so that only this is something we want. All right, so in case you are very interested in MIL music information retrieval, there is a textbook, a whole textbook for that. And of course, you're not going to buy this textbook from Spanger, so you can also access their notebooks from there, free of charge. I actually create a whole 3,000 level course from this textbook, so it's wonderful. And I believe you can go even further into postgrad levels. And well, 5 minutes left, and I'll try to add something more to the melody using another library called Music 21. So this is especially useful for music analysis and creation. So it comes from one of the music labs in MIT. So in this example, we are relying on the open source software called MuseScorers to display music. And the one good thing is that, well, it's open source, right? So people can make all kinds of adjustments to it, and you can even apt-get install it. So it's wonderful that all the outputs can easily be attached into Colab. So it's good for education and also some other kinds of information uses. All right, so the notes that I have created actually can now be read into Music 21 library, and it looks like this. I don't know why this show media is coming up. So it can also be played right inside this environment now. So it's not very good alignment because I sang badly, unfortunately. And well, it sounds too low because for a male voice, it doesn't sound like what you would expect. So I transpose it to higher. So this requires a little bit more work in music. I hope that somehow you recognize the melody after I play so many times. And it's still a little bit boring. Let's add some second parts to it. And by adding another melody 2, with a third minor lower, it can create a new music. Okay, some nice music coming up, but let's try to analyze what keys this is. So Music 21 provides very good facilities for analyzing the keys as well. And also we can try to put down some, we try to remove some of the accidentals so that it sounds better in the key. And well, it's not good enough. Let's add some bass part as well. And it can sound like this. Insert the bass. And then let's take a look into the score. So this is the music we have created. Okay, we got to wait when this message disappears. I think it's almost there. Hey, come on, this is our final demo. Well, it's okay. Oh, it's there. Yeah, it sounds pretty modern and nice to my ears. So definitely you can make it a lot longer when you are able to sing longer, when you are able to make more interesting musical deviations using a lot of the facilities provided by Music 21. It is a huge library. Even the tutorial has turned more than 30 chapters. I haven't finished reading yet, and yeah, you can try to take a look into that. So after all, how are we able to teach the machine to be creative? It's about exploratory, combinatorial, as well as transformational creativity if you really want to make something fun with computer and creativity. So there are a lot of things that machine learning and AI can do, but I choose not to talk about this because everyone is doing AI already. You can find huge numbers of AI tutorials. So I increase the links here. You can check it out yourself. And indeed, a lot of things can be done, and we are hoping to call for more enthusiastic coding musicians and musical coders because, well, to be honest, I need some more people to be taught by me in the undergraduate courses for computer music as well, so that I can open the course, of course. All right, so I guess that's all for my talk today. Thank you very much, and in case you have questions, feel free to talk to me about anything.
So we have a few minutes. Are there any questions for our speaker? I think there's one.
Hi. Yeah, Suno. It's very powerful. Well, definitely. The problem about open source project is that you do not have the commercial database, commercial data sets. After all, a lot of artificial intelligence and machine learning tools, they depend on huge amounts of data in order to train something that is realistic or useful. And nowadays, talking about open source does not help a lot in the AI community and AI development because it is really about open data that is necessary to create the same quality useful outputs. But definitely, if there are more devotion into this kind of research or development, I believe there can be better results into in the open source community as well. Yes.
Thank you very much. So for choir or when there is combination of music tone, could you enlighten us how to divide those tones? Because sometimes when we heard a choir, we would like to know the soprano, tenor, what are they playing?
Yeah.
Yeah. So how to do this? It's very difficult.
Yes, indeed. This is still very difficult, unfortunately, and that's why we said we still need a lot of more research in this environment. So some of the mathematical ways are like to decompose the spectrogram into different sets of multiples so that we can find the pitches, because we actually are able to find them as integer multiples. So for example, if this is 100, we have lines of 200, 300, 400, 500. And if we have another note which is, for example, 60, Then we have 60, 120, 180, etc. So it's two series of numbers which can be mathematically separated. And nowadays, using some deep learning tools, it can somehow do good results in source separation. So there are already some deep learning frameworks, for example, splitter, which are able to separate sounds of different tone color. But for choir, it's very difficult because human voice is kind of similar when they stack up together. So it's still a big mess for computer music people. So if we are able to find more researchers in this field, that would be wonderful. Yeah.
In this demo, you're trying to use the single track to
Yes.
to the presentation. But I would like to take a try on some YouTube music and download a sound, download a video to this demo. Is it possible to separate the music?
Totally impossible. Yeah, unfortunately, because the methods that we have used here is called autocorrelation, and it's only able to detect monophonic sound that is only one single melody, not even a piano chord, so you cannot really detect it. So here it's going to use the autocorrelation tool, which is good for one single melody. So for multiple sounds at the same time, simultaneous sounds, another set of techniques is required, and yeah, I couldn't try to make this more complex, so I chose the easier way here.
Okay, if there are no more questions, let's give another round of applause to our speaker, Chuck-jee.